This is example 113 from the course text, and the idea is how you can use the bounded input, bounded output criterion. You can use this criterion to characterize the system if it is stable or not. Okay. So what we've discussed previously is that for stability, if a bounded input leads to a bounded output, the system is stable, not otherwise. Okay. So you see, if you suspect if the system is unstable, then a useful strategy will be to verify this, is to look for a specific bounded input that leads to an unbounded output. Now, if that is the case, if you have a bounded input and the system performs operations or transforms the input, and it transforms the input into an unbounded output, the output is divergent, then finding one such example enable us to conclude that the system is unstable. Okay? So if this criterion does not hold, the system is unstable. If the output is divergent, if the output is not unbounded for a bounded input, well then yes, the system is unstable. So, but in cases if such an example is doesn't exist or it is hard to find, then we must check for stability by using a method that does not utilize specific examples of the input signal. So to illustrate this approach, let us check the stability of the two systems. So we have two systems, S1 and S2. Now S1 is defined as yt equal to txt, right? So for the first system, we can seek a certain, we can let's try to seek a specific counter example in order to disprove the stability. So we might try a simple bounded input such as a constant or a unit step. You see, unit step is a bounded input. Okay, u of t, the magnitude of u of t function for time t greater than or equal to 0. The magnitude is always greater than 1. Okay, for t greater than or equal to 0, that's always the case. So this is the bounded input. Now what if you apply a unit step function or a constant to the input of this system? What happens is that a constant equal to xt equal to 1, okay, in which case, for example, if this xt equal to 1 for t greater than or equal to 0, then you have ut instead of xt. Okay, so yt will be of the form yt will be equal to t ut. Okay, t ut. So it's in fact a ramp function for t greater than or equal to 0. So this is true. This is for t greater than or equal to 0. Now you must see that as time grows, the output grows. Okay, and the output grows indefinitely with time, forever. So that means the output becomes unbounded, or it becomes divergent. Therefore, this system does not satisfy the BIBO stability criterion. So you can say that the system S1 is unstable. Okay, even for a constant. I mean, if you substitute xt for a constant, the the since you have a function, you don't, it's not a function, it's a multiplier. So the multiplier is the time itself with the input, and this multiplier grows with the time. Okay, so even for an input that is a constant, will yield yt equal to t, let's say with some constant, if its constant is 1. So this becomes unbounded, since no matter what finite constant we pick, the magnitude of yt will exceed that constant for some t, right? I mean, even for this, for the case of unit step function, this happens at t equal to 1. Okay, so at t equal to 1, this is 1, which is the magnitude of the input. Then for t equal to 2 and 3 and so on and so forth, the yt is growing like a ramp function, and it's growing indefinitely forever. Therefore, this the output of yt is going to grow forever. So it's an unbounded output. Okay, so we conclude that the system is unstable. Okay, it's this criterion that we have to check. So that's a specific counter example that disproves the stability. Okay, so one counter example is enough to prove that the system is unstable over here. So let's look into the second example. We have a system S2 given by yt equal to e of xt. Now this system is stable. Okay, S2 is stable, but it's not very easy to find an example like we have said earlier, a counter example. So if find an example that a bounded input leads to an unbounded output. So for example, in the first case, we have a bounded input ut, but the output was unbounded, and this specific example was good enough proof. It was a counter example. You see, you cannot have hundred of examples to prove anything, but just one counter example is sufficient to disapprove. So we have a sufficient evidence for system S1, so to prove that S1 was unstable. But for S2, uh, it's hard to find a bounded input leads to a bounded output criterion example. So for system S2, which is in fact stable, we would be unable to find a bounded input that results in an unbounded output. So let's not go for that example. So what we do is we proceed to verify that all the bounded inputs results in a bounded output. Okay. So what we do is specifically, we don't assume any input signal. We say that, okay, let B be an arbitrary positive number and let xt be an arbitrary bounded signal bounded by B, which means this is the definition of the bounded signal. The bounded signal is it's nothing to do with the length of the signal. I mean, this x of t can exist. This could be a cosine sine function. It can exist forever. I mean, for all t's. Uh, it could be any arbitrary signal, but the magnitude should be bounded. The magnitude of xt for all t is bounded. Okay, so for all t, the magnitude of xt is bounded. This is the only assumption we are making. So we are making no other assumption about xt except that the magnitude is bounded. Okay, or this can be written as xt is bounded by is greater than minus b and it's less than capital B. Okay, for all t. Now using this definition of S2, this is the system that is being defined by this equation. We can see that if xt is bounded, then yt must satisfy the bound of the yt must satisfy e minus b to e plus b. That means that the output y of t is bounded by exponential b. Thus, the system S2 is stable. Okay, so we conclude that if any input to S2 is bounded by an arbitrary positive number b, the corresponding output is guaranteed to be bounded by E of B. Okay, that's all.